All right, well, welcome everyone. We're on BART webinar 7. Really glad that you could join us. So this webinar is on non-Cartesian MRI reconstruction, and Moritz and Christian were both prepared the material and they'll be presenting it. I'll get started just by sharing my screen before then. I just wanted to open. Can you see the BART webpage on my screen?
Yes.
Yeah.
Yes.
Great. So I just wanted to show real quick the BART webpage. We've made a few changes. In particular, we've kind of sectioned the website into various different tabs, and this is kind of part of ongoing work to revamp the documentation. But under webinars, we have all of the webinars so far, including webinar 7. This takes me to the GitHub, where Moritz and Christian will be presenting from. So we have here essentially the schedule and links to the notebook and to Colab for webinar 7. I just have a few points I wanted to make before we get started. So today we'll talk about a deep dive into non-Cartesian MRI reconstruction with BART. Moritz and Christian will go over how to set up BART using the NUFFT command, which is really the workhorse for our non-Cartesian work, and then how you can perform parallel imaging non-Cartesian reconstruction. And then they'll also talk about some performance considerations when using these non-Cartesian tools, and then we'll have a small exercise for you to participate in, followed by Q&A. A few brief updates on our end. We recently released in September version 0.8.00. This has a lot of really exciting updates. You can download it, as well as see the fuller list of changes directly on GitHub. But the main highlights of this newer version is the introduction of the machine learning tools, which are summarized in the recent MRM paper, Deep Learning with BART. And actually, the webinar 6 material goes into this quite well. So check that out. There's TensorFlow integration as well, ongoing performance optimization, as well as tools for doing more sophisticated block and EPG simulations. This goes really well with a lot of the model-based reconstruction features recently added. Next week, December 8th, well, actually December 5th through 12th next week is the MRI Together workshop. It's free to attend and sign up. And the BART team will be presenting on December 8th on maintaining scientific open source software, 10 years experience from the BART project. So check that out if you have the chance, and if you want to try to see what goes into creating this type of scientific software, and also how you could possibly contribute either to this BART project or your own. And as I mentioned, we've updated the website. We've organized things into more distinct sections, and we hope to have this as part of the ongoing documentation. Okay, so without further ado, I'll hand it off to Moritz and Christian. Just a reminder, you can follow along directly if you click this Open in Colab link. And so you do require Google sign-in, but this will let you interactively follow along. And since we are, I guess we're up to a larger group, but please feel free if you have questions, just politely unmute yourself and ask, or use the chat, and we'll try to answer those as we go. But anything before we get started? All right, Moritz, do you want to get set up?
Then I think I take over. So yeah, welcome everybody also from my side. As mentioned, we start when I share my screen. From the BART webinar site, you can start to use this Open in Colab badge to go to Google Colab, but you can also run that notebook locally on your computer. And there maybe you already have set up BART, but here we of course need to set up BART on Google Colab, and that will take some time. We go through that by running the setup. Let's see. Yeah, so there are some issues with old versions of GPUs on Google Colab, which are not supported by CUDA 11, which is installed. So if this is the case, we need to go to CUDA version 10. And also what we do here is we just check out the BART webinar. Oh, that's wrong, but shouldn't be a problem. So you will check out or you will copy the BART webinar from the BART webinar site, the GitHub, and we will CD into that if you're on Google Colab. That is to get the data which is uploaded on GitHub. And we.
Moritz, can you make it a little bit bigger?
A little bit bigger. First of all, I can do full screen like that, or too big.
Yeah, that's good. I think that's good.
Okay, I'm sorry.
There we go.
So if you look on the site, we just checked out the BART webinars and we CD'd into that webinar 7 folder where we have now our data, like some exercise data, some figures used in that notebook, and some data we will use later. And then the second step is we install the libraries needed for BART. There are not many dependencies, so we need GCC to compile the FFT, so FFTW3. OpenBLAS and some tools, but it went here fast. Close that at the side again. And then, of course, we need to download or clone BART in our local, on our Google Colab installation, and also compile it then. That might take a minute again, but it usually is pretty fast on local machines.
Right, and all of these steps can essentially be done if you want to really quickly get BART up and running for any reason, not necessarily just for this webinar.
Yes, exactly. But yeah, compiling takes some time. Probably much better than compiling other toolboxes, hopefully, but I mean, I'm not sure if anybody of you tried to compile TensorFlow. Then I would need to go to get a new coffee now. Okay, we are done. So now we have BART, but we need to add BART to the path variable so that we can really call it from the notebook. And finally, we see we have BART. It's now installed in the BART webinars folder, webinar 7. There we cloned BART, and we have this BART binary, and we are at version 0.8. Yeah, for later, we just create some plotting functions in Python, which are useful to show images. And this was basically the setup of BART. So that leads us to the second and maybe the first important chapter of this webinar, the non-uniform FFT in BART. And there we want to start with the definition of the non-uniform discrete Fourier transform. And it's provided here, and it's kind of important that we state that here because there are sometimes problems when people want to use provide their own trajectories because they are from toolbox to toolbox, they are scaled differently. But from our conventions, what we have here is basically the unitary centered Cartesian FFT. If we take the coordinates, the trajectory to spread from -n½ to +n², then it's basically the same as the unitary Cartesian FFT. And the interesting thing about our scaling of the coordinate itself is also that basically our coordinate or the k-space coordinates are given in units of 1/field of view. And you can then estimate from the trajectory itself directly the field of view or the grid size you want to use for an optimal reconstruction. Yes, so I unfold this now. Because I just started to talk about the trajectory, because we, of course, have tools to create trajectories in BART. And these are basically files holding complex float numbers. And there we follow some conventions, of course. So in the zeros component, the zeros dimension of this file, it has always dimensionality 3. So it holds the X, Y, and Z coordinate of our trajectory. And if you want to do 2D imaging, you still need a Z coordinate, but it's always 0 then. Then in the second and the third dimension, we have the readout and the phase encoding. But essentially, the splitting between both of these is arbitrary. So you can merge these dimensions, but 1 and 2, or a dimension is saved for that. So we can, for example, easily create a Cartesian trajectory with the BART trajectory tool. I call it trajectory Cartesian. And if we show just the metadata of the trajectory, you see what I just told you. We just have created a trajectory with 3 coordinates, and it has 128 by 128 points. Because we want to plot that in a second, we somehow reduce the dimensionality. So we take n equals 32 now, or 16, I think, instead of 128. And we also show directly that we have, of course, multiple options to generate trajectories. I mean, of course, a Cartesian trajectory is probably the most boring, because you can just do Cartesian FFT then. For creating radial trajectories, we give -r option to the trajectory tool. And then we have plenty of options to generate like different radial trajectories. For example, we can do double angle, and I show you the difference in a second when we plot that. We can directly integrate oversampling factors by giving -o and then the oversampling factor, or we could also, for example, generate golden angle spreading of the spokes. Here I just create some trajectories files using these various options. For you, maybe, I mean, we are doing a lot of radial imaging, but maybe you don't do that. So you want to give your own trajectory, then of course you can create the same file with different methods. So for example, you can use Python to generate your own trajectory. And here I just have one short Python cell, which generates a spiral trajectory with multiple interleaves. And so it basically, okay, we have generate some NumPy arrays here, which have the spiral coordinates. And in the end, we use the CFL.writeCFL function, which comes with the BART installation, and to write down the NumPy array to the BART file format to CFL files. So we generate one spiral trajectory for visualization and one with more sampling points for later use.
Moritz, could you, in this function, could you print the shape of the trajectory so we can see what it ends up being before you actually write it to a CFL?
Sure, I hope. And I hope I don't just destroy everything.
That shape.
But
yeah. Right.
So again, I mean, here we have the 3 coordinates in the visualization, 80 points per spiral, and I think 3 interleaves. And in the larger one, we have more points per spiral and a little bit more interleaves, exactly. So finally, we are there. We have generated different trajectories, and we can plot them. So that's just matplotlib for plotting. It's maybe not that interesting, but the images in the end are hopefully. Actually, can you see the spiral, or is it Zoom which is in the way from my side? No,
we can see it.
Okay, great. So you see, we created a Cartesian trajectory with multiple straight lines. As I said, it spreads from -n½ to +n², which is 8. So n was 16. We generated the radial trajectory where the angles are drawn from 0 to 180 degrees. Or if you use the radial trajectory with dumbbell angle option, you see the the angles, the interleaves are basically spread it in 1 to 2 pi or 1 to 360 degrees. With the oversampling option, we just sample each spoke more densely. And finally, we have the spiral trajectory on the right side, which was just generated with Python. If we have trajectories, of course, we also need the k-space on the non-Cartesian k-space sampling points. And here we try to have the same dimensions as for the trajectory, but of course we don't have 3 coordinates, but just one sampling point. So the 0 dimension is always 1 for the non-Cartesian k-space, and then in the 2nd dimension and the 3rd dimension we just have the same dimensions as the trajectory has. And here we just generate some k-space data. We use the BART Phantom tool. It has a k-space option, and you can then provide it also a trajectory, so -t trajectory, and then you get the k-space. It's a nice tool because it has like an analytic representation of the Chaplogan phantom as ellipses, and analytically computes the k-space points at the given coordinates. And you see here again, like the dimensionality then. So we plot the metadata of the k-spaces. You see, as I said, in the 1st dimension, it's always a 1. And then we have the same dimensions as for the trajectory. So now we have the coordinates, the trajectory, and the k-space. How can we use that? And that's the BART NUFFT tool, which does the non-uniform fast Fourier transform. And it basically has 3 modes. The first mode is the forward mode. It maps from image space to k-space. So if you have some image on a Cartesian grid, you can generate the non-Cartesian sampling points from that, and maybe more like in a mathematical way. So the k-space is the non-uniform FFT of the image. That's the normal mode of the NUFFT command. We have the adjoint command, which is usually sometimes also called gridding. So it basically applies the adjoint NUFFT on the k-space, which is an input to map to the image space. And then as a final option, or final very important option, we have the inverse. So we can also compute the inverse of the NUFFT, and that is done iteratively by solving this least squares problem here. So the least squares inverse problem to generate the image. So when I start now with this NUFFT tool, first I want to show you the NUFFT tool just for the Cartesian k-space we just generated. So we have the Cartesian trajectory, and we can then do the adjoint NUFFT on it to basically get the image of the Cartesian trajectory. But the cool thing, because our convention is just the same as for the unitary scaled Cartesian FFT, we can just use the same data, the Cartesian k-space data, and just do a Cartesian FFT on it to just do the same, to generate the same thing. So no magic here, but to show that it's equivalent, just run that cell. We do the adjoint NUFFT and the Cartesian NUFFT, and okay, the images are already there, but I still plot it again because it hopefully works. And you see there's no difference. We have up to some float point precision, hopefully. There's no difference if we do the Cartesian FFT or the non-Cartesian FFT. The only thing is, we are in other dimensions because the k-space was stored in this other dimension. So we, for the Cartesian FFT, we still have the 1 in the 1st dimension, but in this the 2nd and the 3rd dimension, we have the Cartesian image. Of course, that's maybe a little bit boring because we're Cartesian. So we go now to the non-Cartesian case. We look at the radial trajectories. And there you should know or might know that the simple adjoint doesn't work because we need to compensate the density, or we need to compute the inverse if we have sufficient amount of sampling points. So what we can do is still we can run the gridding. So just do the adjoint NUFFT on our radial k-space using our radial trajectory. But then if we want to do density compensation, we should compute this from Luck filter. So we can do that. So it's basically the trajectory up to scaling. It's the magnitude of the coordinates, which we can compute with the BART RSS command, which computes the magnitude if we do the RSS over the X, Y, and Z components. So in the second step, we multiply the density compensation with the radial k-space, and then do a joint NUFFT that will give you this gridding solution in its radial density. Or the other options is that we just directly compute the inverse with the iteratively solved least squares problem by giving the -I option. We don't need to do any density compensation. We get the inverse reconstruction. And this, I mean, I'm not an expert on Spiral, so I don't know exactly how to compute the density compensation. It's possible, I guess, but it also works straightforward if you just do the inverse NUFFT on the Spiral data. So you can run all that. And also here, no surprise, the images are already there. But if we don't do density compensation, everything is blurred a lot. With density compensation, it looks nice already here, but it's the same if we just do the inverse or similar, and the inverse also works for the Spiral data, where I have a little bit more artifacts, but I mean, the trajectory is also different. In the beginning, I said that the k-space or the trajectory itself is given in units 1/field of view. And I just also said, like, from that we can then estimate the image coordinates or the grid size of the image. We can use that also to change the field of view by just scaling the trajectory. And this is quite nice because then we can do oversampling or stuff like that, or resizing the field of view retrospectively. So
Moritz, before you go, just to quickly check in if anyone has questions.
Oh, sure.
But hopefully you can see that there's no requirement to use our trajectory. You can make your own, and the reconstruction is still the same kind of process. Okay, so some questions or comments? Steen, did you have a question?
Yeah, I can ask a question there. So often when I do my gridding, I have a different trajectory where I don't have the easy access to the analytic, and I do kind of like the pipe method and maybe like iterate over it and to get the density correction. And I often choose that because for the if I do 3D reconstructions, I don't want to iterate too many times on it to get the density correction, or even do the full inverse. Are you able to maybe comment a little bit on that? How would you do that, and what is your experience with doing it one way versus the other?
Yeah, we have that. I think Christian will show that for the full Pix command. Do you? The density compensation?
I will show how to use density compensation as weighting and parallel imaging reconstruction. Just as like
yes, exactly.
To speed up reconstruction, especially in 3D case. But if I understood you correctly, you are doing iterations for the density to get the density compensation correct. Did I understand that correctly?
Yes. No, normally, if you have, say, you're in a golden angle, or trajectory or anything like that. You normally do a couple of iterations where you basically take the one, you grade it back and forth and whatever multiple times to get the correct density correction.
Yeah, we normally don't do that because normally we don't use density correction at all. We just use the adjoint and a parallel imaging reconstruction directly, which works as well without doing anything with the density compensation. So that is only, I think the only case where we really care about that is for large 3D data sets, where you have a problem that you don't converge. But I think so far we have not used anything more involved than a Ramlak filter in that case as well. So currently there are no real tools to calculate, like more advanced tools to calculate density compensation in BART.
Yeah, but I think
I saw somebody also just posted the paper in the chat.
yeah, there's some chat discussion in the tab, but if I understood, your question really is just what's the trade-offs? Like when would you recommend, if it's 3D, doing full iterative versus density compensation, and like if you have any practical experience with that trade-off?
Yes, but I guess my question was also towards that. I mean, A was like, how can you do it, or how would you do it? And then the other one is just like, well, what is your experience with doing that inside the BART framework? So.
Yeah, do you guys have any experience with really 3D non-Cartesian? And
no, I must admit I don't have. But
yeah, I think it's a good question, and it's asked a lot in the mailing list. And I think that yeah, running it iteratively is often not computationally like feasible, and so some form of density compensation is useful. There's various preconditioning methods that also can help. I'm not sure to what extent we have those right now supported.
No, I think we're still a bit at the beginning of how to properly supporting 3D reconstructions. So we might include something like that in the future once we basically either once someone else donates an implementation, or once we run into issues and implement it ourselves. I think so far also large 3D NUFFT large 3D non-Cartesian reconstructions also were a bit hampered in BART by something we're going to talk about later. For speed considerations, we basically had 8 times larger arrays. Is that correct, Moritz? Yeah. The factor, which was a bit of a problem with memory if you do 3D pushball, for example. And we only just recently basically got that under control. So
yeah, I just want to point out the comments just so everyone sees. So Kwanjin, you mentioned that you weight the trajectory, you weight the k-space data with the adjoint reconstruction. You use that as a density compensation. Is that my understanding?
Yeah.
Yeah.
That works better than inverse. I don't have any success with inverse FFT. I mean, inverse NUFFT.
With 3D or with 2D data?
It's a 3D.
Oh, with 3D. Okay.
With 3D, yeah.
I don't have much luck with the inverse mode. But when I weight with adjoint before, I mean on the K data itself, then it was much better with the NUFFT option.
Yeah, I will talk about that shortly. The problem is just the really bad conditioning of the problem. So yeah, basically you could iterate forever and still not really succeed. So some kind of basically improving the conditioning of the problem is a good idea, and weighting it with the adjoint. Using the adjoint and weighting the k-space data before NUFFT is a good idea in that case.
Yeah. Yeah. So then, there's a link by Martin to a paper on density estimation, and then as well that Tobias Wood has a 3D non-Cartesian tool called Riesling that can also be good for doing these very large scale problems. All right. Yeah, so good questions, please keep them coming. But basically so far, how to create trajectories and how to use them for NUFFT. All right.
Yeah, just one point. I'm not sure how often it's used. I never use it. There is a preconditioning option for the inverse NUFFT, which is, I think, preconditioning based somehow also on the PSF. So maybe that helps. Could just try, but I don't completely know what it does. So
Yeah, we could play around with that at the end after the exercise and kind of see these trade-offs.
Yes. Okay. Great. So then I come back to where I was. That is that we measure the trajectory in units 1/field of view, and we can then estimate the metric size of our reconstruction from that, which is optimal for the given maximum k-space measured, the highest frequencies. But then we also have the option to specify the grid size instead of estimating it. So for the normal field of view, here we estimate, or we provide the grid size, and it's twice what is here. So here it was 128, but that does not change the image at all. It just computes the image on a larger grid, and you can think about this as, in the Cartesian case, zero padding. So we keep the frequencies in the range from minus 64 to 64, and then zero pad to minus 128 times 128. Instead, if you want to change the field of view, so there you will need to scale the trajectory. So for example, by scaling the trajectory with a factor of 2, we get a larger field of view by a factor of 2. Yeah. So we can just do that and run that. And as you see here, the plots which have been already there. So say again, this is normal. The image size goes from 0 to 128. If you provide the DIMS, the 256 by 256, it goes from 0 to 256, but you don't gain anything. So you don't have really a higher resolution. But what you can do is you can go from 0 to 256, but for the scaled, you see that the field of view is larger. Another cool thing which you can exploit for the non-uniform FFT is that you have properties for shifting the image, and also, I mean, you can also do the shift in the Cartesian case, but you can especially do it in the non-Cartesian case. And what you can only do in the non-Cartesian case is that you can do rotations by rotating the trajectory. And yeah, so you need to multiply the phase on the k-space sampling points to do a shift. And yeah, you can just rotate the trajectory to rotate the image. And here I just show you some examples where in the first case we now just start generating our Chaplog and Ventrum on a larger grid, on an oversampled grid, to really be able to move it. So the image then is just a reconstructed image, but here, interestingly, we can just create the trajectory and rotate it by 45 degrees to get a rotated trajectory, and then we will do a rotated reconstruction. Or we have the tool field of view shift in BART, which gets a trajectory, at least for the non-Cartesian case, and then you can provide a shift, which is again measured in units field of view to transform some k-space to the shifted k-space. And then again, if you do the inverse NUFFT, I already run that, you will see that you can shift your reconstructions. And this is quite nice, and you will try that in the exercise if you want to, of course, because if you maybe have a measurement where what you really want to image is not in the field of view, or not at the center of the field of view, you can just shift it to the center and then reduce the metric size, and your reconstruction will be faster because you do computations on a smaller metric size. So that
There's a
was
question. There's a question in the chat about the field of view shift. So based on the way this is implemented, would this work for other trajectories, for instance, like a ramp sample trajectory?
what should be the
I
difference?
think essentially that the samples are not equispaced. Is that the point?
So
Yeah,
if,
basically.
yeah,
that they're not.
then it should work. I mean that field of view shift tool just gets a trajectory, and basically it needs to trajectory to compute that phase where we need to shift. So it needs to compute the dot product of your shift and the coordinates, and that's it. So it should work with any trajectory. Yes. So it's also not black magic, but it can be quite nice to be more performant on a smaller grid. Are there any other questions? Because otherwise, I think we have a speaker change. But I'm not running away. So
There's another comment about field of view shift, applying the shift to the case-based data itself. So your field of view shift is applying it to the case-based data, right?
exactly.
So I think what you're describing is the same feature as what BART is doing. So yeah, okay.
So here, the field of view shift, you need to provide the trajectory if you're non-Cartesian. You need to provide the shift. How far do you want to shift? And then you will give a case-based data of the unshifted case base, and you will get the case base of the shifted or the shifted case base. And then after that, you can do the inverse NUFFT to get to image space. But of course, I mean, you can also do an image reconstruction and then do the shift with on the Cartesian grid. But then you don't win anything because you did the non-Cartesian reconstruction on a too large grid, basically.
Yeah, I think the main point to make here is that for the rotation, you're actually creating a new trajectory. Right? You're rotating the coordinates of the trajectory, whereas for translation, you're scaling the case-based data by a linear phase.
Exactly.
Right. So one's modifying the trajectory and one is modifying the data. There's a question in the chat if you can provide shift values for each point or readout in case space. For instance, self-navigated respiratory motion correction with radial sequences would possibly have a different shift for each readout.
Different shift for each readout. I mean, if you want to do that, you can split up the trajectory and the case base, and then apply the different shift on each sampling point. Basically, I mean, you can do it independently on each sampling point if you want to. So you need to split your data, do it, and join your data back.
Yeah, that's a good idea. So you would basically, or Christian, you want to make a comment?
I want to say, like this is not yet really what the tool is supposed to be used for. It's like shifting the entire case base at once. So if you want to like shift parts of the case base because you know exactly where your values should end up, then yeah, you can do it with this tool like by splitting it up, but it's going to be a bit more difficult.
Yeah, I want to make a comment on that though, and I think that the spiral trajectory was a good example of this, but you know, it's quite natural to mix small scripts of your own with these various commands. So you know, you could in principle, because you know which points or readouts need which shifts, you could in principle write a script that splits the data, calls field of view shift, and then rejoins the data, and then just work with that script now as your high level tool. So you know, just because the tool itself doesn't have every possible feature doesn't mean that they can't still be combined in these powerful ways. All right.
Okay, then let's continue. No, so let's share screen. Wait, can I somehow steal the screen sharing?
I just stop it.
This will stop. If you stop voluntarily, then this works better. But
We've been going for about 40 minutes. Do we just want to take maybe a 5-minute break? Kind of the halfway point?
come on, Zoom. Yeah, we can. I mean, we're a bit slower than we expected. There were
Slower?
a few
Okay.
more questions, but I think we're still fine.
Okay, so let's just take a quick 2-minute break just to give people a chance. So we'll start at 42 after the hour, just a couple minutes. Yeah, and then Christian, on yours, the Zoom bar ends up interfering as a black bar.
Yeah, Zoom somehow, like, I wanted to share one desktop and Zoom decided to not like what I was trying to do. I somehow also lost the chat for some reason, and
I'll keep an eye on the chat. The other thing is if you could zoom in a little bit. That's good.
This is probably better. Okay.
Yeah.
Hi,
All right.
Christian. What is the musical instrument between two guitars?
That is what do you call them in English? There's what they play in Scotland. What do you call them?
Bagpipe.
Bagpipe. Yes, that is a bagpipe. My partner's bagpipe.
Thank you.
Okay, but I think we're after this. Yes.
Yeah.
Then let's continue. Okay, so as we already talked before, the one problem in imaging can be that if you do 3D imaging, that the problem just becomes very badly conditioned. God, Zoom, you are driving me crazy. Okay, there we go. It can become very badly conditioned. And one example, as we just already heard, is to basically weight the trajectory, weight the case-based data with the density compensation before. And that is basically what I want to show in the first example. So what we do is we create a radial trajectory, 256 samples, but quite well conditioned. So it has 127 spokes. We create a phantom of that. We want to use a parallel imaging tool. We want to use BART-Pix, but we don't really want parallel imaging. So we just create once as sensitivities because it really wants a sensitivity matrix. And then we only give it 3 iterations and see what happens. This is basically in 2D, what could happen in 3D is you get some blurry result. In 3D, it will look even worse. And the idea is just, okay, we can improve the conditioning and thereby the quality or the speed of the reconstruction by using the density compensation as as a weighting matrix, and we do exactly that. We, into the same idea as Moritz said before, we use the RSS to get basically a Ramlak filter from the trajectory. In this case, we want to use the square root of it, because actually in Pix we apply it twice, and then in Pix, so this is actually the Ramlak filter, what it looks like, that we use, or the square root of it. You can see it's basically 0 in, or close, small in the center. It becomes larger the further you go out in K-space, and then we can give it to Pix in as a weighting matrix or as a pattern. It treats both of these the same, and we also use three reconstruction steps, and we can see, okay, we get a much better image already after 3 steps, which is basically how we can see that we improve the conditioning of this problem.
Christian, can you go a little bit slower? So you plotted here the result of running Pix.
Oh yeah,
Can you go to the-
this is the result of running Pix once with, so left is the same image we saw before, the blurry image using without any weighting, and the right is using the Ramlak filter as a weighting matrix in Pix.
Right, so can you just go back to the Pix command that you
Yeah.
ran, so we can quickly digest
Oh yeah,
that?
it's just this.
So first, yeah, maybe you could point out that it's also running on GPU.
Oh yeah, it's running on the GPU. It doesn't really make any difference. I mean, how long does it take? It takes 0.8 seconds. It would have taken the same time on the CPU, but I like it. I gave it iterations 3. I tell it you can only have 3 iterations. I use the pattern or weighting. It treats those the same. This square root of the Ramlak filter. I give it the trajectory, our radial K-space that is the same. The sensitivities is just a matrix of ones. We only have a single coil in this case, which is just once. So we don't really want to do parallel imaging. And then get this as the output, which I plot below.
Right, so if you have a density compensation that you've computed, this is how you would pass it through?
Yes, this is how would I pass it through.
Mm-hmm. Okay.
And as you can see, it like improves quality after 3 steps. If we run it for a reasonable amount of time, like give it 30 steps, which is the default. I've done this here, so basically these are the same commands now, just with 30 steps each. We can see, okay, we now basically get the same result. So we improved the conditioning, but like we didn't really change the problem too much. We can see that we did change the problem a bit, but I'm not sure if it's really possible to see it, but we have a bit more artifacts in the weighted K-space, where we use the weighting, Ramlak weighting. This might get worse. So it's actually, it's not noise optimal to use the Ramlak filter in this case, but as we heard before, in 3D imaging, you sometimes just can't get any good results using the inverse NUFFT, or in the same problem with Pix might appear. Then it's much preferable to have this be a bit less noise optimal than to just have no good result at all. But that was just as a quick aside. What I really wanted to show you is how to do parallel imaging in the non-Cartesian case using BART. So for parallel imaging, I mean, kind of by definition, we need color sensitivity profiles. There are quite a lot of options to calculate color sensitivity profiles. Like we could use a separate Cartesian pre-scan and already know our color profiles. But it would be far more pleasant to just use our just acquired data, our non-Cartesian data itself. It should work well, especially if we do radial or lots of spiral sampling, because the K-space center will be densely sampled. So we'll basically have a good calibration region. It's just not in a format that works really well. For example, E-calib only, or the E-calib, which is the BART implementation of eSpirit, only works on Cartesian data. So yeah, I want to show how to use E-calib on non-Cartesian data as well. Yeah, this will be using a spiral data set, which was acquired as part of the first ISMRM reproducibility challenge, where groups from around the world try to reproduce CG sense. Yeah, this is almost already in BART format, so you can see sometimes data sets in the wild will almost use our format. So you can download it from this link. It's this raw data spiral ETH.h5, probably because it was acquired in Zurich. And we find it has the following dimensions. So the dimensions are 27,003. By reading the paper, we find out this is a spiral data set with really long spirals. So one single spiral interleave has a bit more than 27,000 samples and 3 interleaves. The problem is this first dimension, as Moritz explained, BART really wants a 3 there for like x, y, and z, or kx, ky, and kz. But since this is 2D data, we can just extend it by 0, since the kz will just be 0 for all points. So we resize the first dimension to 3, which means appending a 0 in this case. And now we have a good format for BART, which BART likes 3, quite a large number, and 3 again. I also wanted to plot it to really show you what it looks like to have this long spirals. So on the left, this is some uninteresting Python part here. On the left, now that I zoomed in, this is difficult to see. On the left, you can see all 3 spiral interleaves. You can see it's basically densely sampled inside of this circle. On the right, you can see a single spiral interleave where you can basically see how it goes through K-space, and that it does it using a single sampling density, basically all around. Okay, Morris talked that you can normally get the matrix size from just those BART tools will get the matrix size by themselves, just from the trajectory, since they are normally the trajectory is scaled to minus FOV minus field of view half to field of view half. In this case, they fail a bit. I'm not quite sure what the problem is. They give 240, but from the metadata we knew that this field of view here was 220 by 220 millimeters with a pixel size of 1 millimeter. So our matrix size should really be 220. It might just be some scaling issue with the trajectory. I'm not quite sure because I do not know more about how this data set was acquired. So in this case, we will use the NUFFT and just tell it exactly what size we want. And yeah, our basic idea is, okay, if we only have non-Cartesian data, but E-calib wants Cartesian data, then what we will do is we will just grid our non-Cartesian data and then use E-calib on the resulting gridded, now Cartesian K-space data. So what we do is we use the NUFFT in inverse mode, give it the spiral trajectory, give it the spiral raw data, get out some NUFFT of this, then but this is now an image space, so we use a unitary forward and a FFT to get something in K-space. If we take a look at what this looks like, since there are 16 coils in there, we will only look at 3. These are not the nicest coils or anything. I literally just picked 3 numbers between 0 and 16. And if we take a look at them, we can't really tell much, but we can see it kind of looks like a Cartesian K-space. Okay, so next would be, what does E-calib even want, or what options does E-calib have and which might be interesting to us? We can ask E-calib for its options with -h. We see there are a number of options. Most of these will not be interesting for us since we like the defaults. But we know in the end it wants a Cartesian K-space and will spit out sensitivities. And there is one more thing. We only want a single map in this case. So E-calib can also do something called a sub-sense reconstruction, where it uses multiple coil sensitivities and then multiple images, multiple sets of coil sensitivities and multiple images. But here we want to keep it simple, so we give it -M1, which is the only option that we give it. So we use E-calib with -M1, given our gridded Cartesian K-space, and get out some results. And we're also going to look at the same 3 coils. So that's what they look like. I would say they look like reasonable coil sensitivity profiles. If you have worked with eSpirit before, you can already see one thing, and that is they are not 0 outside of our outside of like a single region. So this is going to be a brain data set. So if you look closely, you can already see where the brain is going to be. In the Cartesian case, it would probably do this very well and would be 0 all the way out here in all coil profiles. It can't do that in the non-Cartesian case, probably because the non-Cartesian data is gridded and is not quite as well. What was I going to say? Yeah, just because it is non-Cartesian data and not the real Cartesian data at these points. Then we can do, yeah, the sensitivities are complex. So if I scroll down, yeah, this zooming in, I can see this is like the phase of the same data set. So you can see.
Christian, you should be able to click on the left to the left a little bit of the images there.
Ooh.
Is that what you were looking for?
Yeah, that was what I'm looking for. And I hope people will not be too upset with me if I make it a bit smaller so that we can actually see all of these, because there will be multiple sets of exactly this size. So yeah, now we can see like upper is the magnitude, lower is the phase. E-calib does give complex hot sensitivity profiles. So next, we already saw it a bit, this Pix tool, our parallel imaging compressed sensing tool. We will not really use the compressed sensing here, we'll only use parallel imaging. So Pix actually can directly work with non-Cartesian data, but it does need Cartesian call sensitivity. Well, it does need image space call sensitivity profiles. So let's take a look at what Pix actually wants. Pix has a lot more options. A lot of them are related to different regularization types and yeah, basically all of the compressed sensing stuff. And the interesting part for us, we can basically ignore most of these except for, where's the trajectory? -t, the trajectory here, because we want to do non-Cartesian imaging, and then it wants K-space. This can be Cartesian or non-Cartesian. In this case, if we give the trajectory, it should be the non-Cartesian K-space. It wants sensitivities in image space and will give us an image as output. So that's basically what we are going to use. And Moritz is going to help me. Did you already talk about the triplets trick? Nope. Okay.
Oh,
Ah, that's unfortunate. I thought that was in the part before that. Okay, then we're just going to skip this cell and look at this cell where I do not talk about that. And you will need to come back to this notebook after Moritz did this part, or you might not really be that interested in it. So here we call Pix, give it the trajectory, which is the same thing, the spiral trajectory. We give it the same. Please don't do that. Give it the same non-Cartesian raw data. We want some debug output, which is the -d, 30 iterations, which I don't think I would have need to specify since it's this default anyway. We give it a bit of Tikhonov regularization, and the call profiles we just calculated, and then we get out an image. It's now called a TURB. Don't worry about that. Yeah, it will spit out a lot of debug information interesting for us. It will tell us, okay, we had a bit of L2 regularization. It used conjugate gradient to solve the problem. It took 2.8 seconds. And now we can look at either one of these images and see that it has successfully recovered a brain data set from our spiral raw data. What else can we do with non-Cartesian imaging? How else can we do non-Cartesian parallel imaging using BART? There is the method of nonlinear inverse reconstruction, NLINV. This is sometimes a bit more convenient to use, like Pix needs the call sensitivity profile, so we needed to do this dance before where we grid the data, then call E-calib, and then we could use it. NLINV is a method which simultaneously estimates an image and call sensitivity profiles. So in this case, we can let BART do all of that. Yes, what does NLINV want? NLINV also can take a trajectory, and then it just needs the K-space, either Cartesian or non-Cartesian, in this case non-Cartesian, and then it will give us an output, and optionally it will also output the sensitivities that it estimated. So, yep, in this case, similarly to the NUFFT before, preconditioning in NLINV is a question. Probably, but not as easily. I don't think it's implemented yet to use a weighting matrix in here easily.
I cannot promise, but I think it's there. If you give it as a pattern, or does it then? I mean, if not, it will be soon.
Yes,
we will check afterwards and edit because it's not that complicated.
Yeah. Oh yeah, I skipped that question. Can you compare Pix without sensitivity map? Yeah, I don't know. Giving it one sensitivity map, but yeah, John, you can maybe do that in chat, and I'm just going to continue. Okay, and then basically takes the same thing. Here we do need to provide it with how large we want our image to be. So we give it give it specific image dimensions. We tell it we want 11 iterations. You can use the GPU. We want some debug level, and this is rescale image up and reconstruction. This it just means that we get an image out that is in between. We scale our K space, just scale the norm of our K space to 100, and we undo this by -s. But the interesting part is we give the trajectory, we give it the raw data, and we just directly get out an image and sensitivities. This will also spit out some debug information. It will then show us, okay, it used 11 steps of the Gauss-Newton algorithm with different number of CG steps in between, took 6 seconds. And we also get a nice, that was not what I wanted. We also get out a nice image of our brain here. And if we take a look at the sensitivities, we can also do that. These are basically the sensitivities that NLINV calculated. Here you can see, if you look closely, you can see that they are going from 0 to 440. One reason is that NLINV internally uses a oversampling factor of 2, so it will always calculate sensitivities that are twice as large as the image that you get out in the end. But you can see like that this center part, the center 220 by 220 pixels are similar to the E-spirit sensitivities that we had before. Why I'm showing you the sensitivities? Because one thing that we have increasingly used in our group, and that also other people are starting to use, is to actually in the non-Cartesian case is to actually use NLINV sensitivities and then do a Pix reconstruction afterwards. So you use this non-linear method, which is sometimes a bit more difficult to work with, but only use it for sensitivity calibration, and then use Pix, which is a linear method, which makes it a lot easier to deal with a lot of regularization factors as the final reconstruction to get an image. And that's also what we're going to do here. So what we do is, as I said, the inner 220 by 220 is similar to the E-spirit sensitivities. And so we take that out, we use BART to resize it in the center to 220, 220. And we also normalize them along the color sensitivity dimension, which basically means that in each pixel, if you look into all color profiles, basically each pixel will have a weight of 1. So if you look up here, you can see that there's lots of parts which are quite dark in here. This has changed a bit after normalization, and now they have the correct size, 220 by 220, and we can use them for Pix reconstruction, which is the next step. Here we do the same thing. We also give it the trajectory, the same raw data. Now we give it the NLINV sensitivities resized to work with Pix. And if we look in the end, we can see that using all of these methods, using NLINV directly, using Pix with the E-spirit sensitivities, and using Pix with the NLINV sensitivities, all works equally well. Yes, before I come to my last part, let's look at the questions. Dirk Meyer asked, what are the disadvantages of using NLINV versus Pix? I assume what you mean. Well, Pix is a linear reconstruction method. So if you have some good way of getting color sensitivity profiles, it is just a simpler reconstruction. And sometimes, in quite a number of cases, it's going to be a lot faster. And as it is a linear method, it's going to be easier to integrate regularization factors.
And the regularization factors are integrated. I mean, that's also one point.
Oh, yeah.
In NLINV, we currently only have a 2 regularization on the images.
Yeah, exactly. And then in Pix, we have local overhang, we have wavelets, we have TV in any dimension that you want. So yeah, that would be our
In
advantage.
principle, though, you could add those in, or is it wouldn't be compatible with the algorithm?
Oh, we can add them in. I mean, what NLINV does basically takes the nonlinear problem, it linearizes it around one point. Then you could add the regularization to this linear problem, get a new estimate, linearize again. So we can do that, and we have done that before, and we are going to implement it properly soon. It's still going to be more difficult to work with because as it is a nonlinear method, it will be more difficult to pick the correct regularization parameters, and picking correct regularization parameters is already basically a science unto itself. Yeah, so that would be some of the advantages of the linear method. One nice thing where NLINV works really well is if you want to quickly get call sensitivity profiles from low resolution images. I mean, I talked before how lots of non-Cartesian methods already lend themselves well to getting call sensitivity profiles as the low resolution, as the low K-space or the K-space center will be densely sampled. So in principle, why do this entire reconstruction if with NLINV if we only want the call sensitivity profiles? There could be an easier way, and that is just only gridding basically a low resolution image like 32 by 32, getting call sensitivity profiles from that, and using these call sensitivity profiles. And we are going to use it once using eSpirit and once using NLINV later to show a bit of an advantage of NLINV in that case. So in this case, we're going to tell the inverse NUFFT, okay, we only should be X, sorry, to only grid us a 32 by 32 image. It is going to do that, and we will look at the first coil. So this is basically the first coil image with huge pixels, but just 32 by 32 of them. And we're also going to use another forward FFT to get a K-space that we can then use eSpirit on. So that's the next step. It's the same thing. E-calib, we only want a single map of this K-space, and then we can get 32 by 32 call sensitivity profiles using eSpirit. And again, you have the magnitude up here and the phase down here. And now, okay, how can you use them in using Pix reconstruction? These have this wrong size. We want 220 by 220 and not 32 by 32. So the easiest way of resizing them is using zero padding in Fourier space. So what we do is we do an inverse. Oh, this is technically incorrect. We use a Fourier transform to convert them into K-space. Doesn't matter which way I do this here. Sorry. Then we resize them basically by zero padding them in K-space, and then we do the inverse Fourier transform to go back to image space. And if you don't believe me that it's the same, I would just run this again. And what we get out is call sensitivity profiles that are 220 by 220. But you can already see a bit of a problem here. You can see that somehow they have acquired artifacts. And one reason for that is that the eSpirit call sensitivity profiles are not necessarily smooth. They can have these phase poles in them, and those lead to problems if you just simply scale them up, as we did here. And in fact, if we now use these in Pix reconstruction, same way as before. On the left, you have the image with the previous call sensitivity profiles, right, with the scaled up call sensitivity profiles. We can see that we now actually did get artifacts. So there's suddenly a huge bright spot in here, which wasn't before, which is unfortunate, but which is just a problem that you might face if you use low resolution data with eSpirit. Well, is there a better way to get low resolution call sensitivity profiles? In this case, we can also try NLINV. The only thing we need to change here in our NLINV reconstruction is, well, first, in NLINV, this is not going to be a problem because the call sensitivity profiles are smoothed by a regularization term. We basically penalize high frequencies in Fourier space to get smooth call profiles, but these parameters need to be adapted a bit. if we want to use it for 32 by 32 imaging. So I just changed them here. These are these minus A and B parameters. But after we run that, what do we get out? Well, we get a 32 by 32 image of a brain. We can't really tell anything. But what do the cost sensitivity profiles look like? Well, we can't really tell if they're good, but these are the cost sensitivity profiles and the corresponding phase. If you look at the phase, you might say, well, look at that. There are also phase poles in here all over the place. Yes, but they're only in positions where the cost sensitivity profiles are 0 anyway. They are not, the phase is smooth. And so if we have 0 magnitude anyway, we might as well have a phase pole, and it doesn't change the smoothness of our cost sensitivity profiles. And again, these cost sensitivity profiles are 64 by 64 because they're twice as large as the image that we get out. So what we do here is, again, we 0 pad them in Fourier space and resize them in that way. But now we need to resize them first to 440 and then take the inner 220 by 220 of these to get the correct cost sensitivity profiles. So that's what we do. We use a Fourier transform to get into to K-space. We resize them to 440 by 440. We do the inverse Fourier transform to get the larger cost sensitivity profiles. And then we take out the inner 220 by 220 of these, and we normalize them again along the call direction. And now if we compare them, these our scaled up NLINV cost sensitivity profiles to the previously calculated E-spirit cost sensitivity profiles, I think at least in this part where the brain is going to be, we can see that these are similar coil profiles. Like they both have some stuff at the outside, yes, but here where the intensity is high, we can see they are similar, or the same thing over here, or as well over here. So let's use them. Let's use them in Pix. Now I do the same thing. I give in the trajectory, the raw data. Now our scaled up NLINV sensitivity profiles, and I get out the image here on the far right. And as a comparison, we have the image with the scaled up E-spirit profiles and with the E-spirit profiles calculated from the full K-space. And we can see the outer two images are both of high quality. So why would you prefer the one on the right? Well, if you have if you don't want to basically waste so much computational power to get cost sensitivity profiles, you can use NLINV to get low resolution cost sensitivity profiles, and you can scale them up without any problems since they are guaranteed to be smooth. And with that, that is how much I wanted to say about.
Question is there, you could also, correct me if I'm wrong, you could take the low resolution image you reconstructed, 0 pad that, and then compute the maps with E-spirit.
Not quite sure what you mean. Like,
so maybe I misunderstood, but if you go back to where you created the low resolution, you did an NUFFT of a low resolution, right?
yeah.
Could you then FFT this and zero pad that?
You could.
Before computing
Yes,
E-spirit.
that might work better. In that case, the only advantage would be that probably if you have a large data set, and especially if you have a 3D data set, NLINV is going to be much faster than E-spirit in calculating cost sensitivity profiles. And that's just
the thing is one option is to do an NUFFT, inverse NUFFT onto a very small grid, and then FFT 0 pad and run E-spirit. And then the other option is just to do NLINV directly on the low resolution.
Yes, but in that case, you would need to scale up the cost sensitivity profiles using 0 padding.
Okay.
But yeah, that's one reason why it is attractive to use NLINV. Like if you have a large data set, if you basically 3D data or high resolution 2D data, using NLINV in such a way might be a lot faster for E-spirit. One problem with E-spirit is just that, well, it does use. Just a second. One problem with eSpirit is that it uses the SVD internally, and SVD of really large matrices is just a problem.
There was a question about, is it possible to correct B0 and homogeneity in Pix, given a B0 field map? I'm not sure if we support that, or if you would be able to just put it directly in the maps, the B0.
I know that we have it for our model-based reconstruction tools.
Mhm.
At least I'm pretty sure, but I'm not sure whether we have that in Pix. I mean,
Yeah, we'll have to get back. In principle, it's possible, but it may not be supported right now.
let's see. I don't think we have it as a normal option, and I don't think we have it as a hidden option either. Yeah, I don't think we have B0 correction right now.
Mhm. Okay. Any other questions? Okay,
And I would say we switch back to Moritz for the last part.
all right.
Okay. I
Mhm.
do lose presenter rights, or did I need to steal it? No, it's okay. Okay, so the last part is a little bit about performance and memory optimizations. As Christian already told, it's just came lately to us that we worked on memory optimization of the NUFFT, and also some optimizations on the FFT, at least on the CPU. And there are like the thing of, or the problem of the NUFFT in 3 dimensions is that you usually need to oversample your grid. And if you think about a reconstruction where you have, for example, already metric size 256 to the power 3 times whatever 8 coils, then these coils and corresponding the coils image already take up 1 GB of memory. And then if you think like that you need to oversample all of these spatial dimension by a factor of 2, then you get to 8 GB of memory. And then you need that not just one time, but multiple times. And then you're maybe at 24 GB of memory. You just need to compute the sense forward model if you do it naively. But now we worked on that, and we worked on the FF2 performance, FFTW performance. So I mean, there's nothing basically you need to really consider. You can just use the options, and it's sometimes a trade-off of memory and speed because of parallelization. So usually, if you don't use a low mem mode, you might get better parallelization. So you might be faster, but that doesn't help you if your program doesn't fit in your memory or even on your GPU memory. So one thing I want to say, it's just FFTW wisdom. That is, from the there are some words on wisdom from the FFTW project, and the idea is that FFTW can measure for your computer what is an optimal FFT algorithm. And there are different modes, but like if you start with FFTW measure as a mode, it takes some time to find the optimum algorithm. But then there's the option to do that and to save what you stored for performance measurements. And we now implemented that in BART. So you can use just the BART use FFTW wisdom environment variable to be 1. Then if you run first time your reconstruction, it might take a little bit longer because it just measures what is the optimal algorithm for the FFTW. But afterwards, it stores that in your BART directory and you can reuse that. It really depends on the CPU you have. Like sometimes it just measure it doesn't bring any performance benefits, but sometimes it does really bring performance benefits. To just show you, I mean, I think I just checked it out on Google Colab, and there it doesn't bring anything, but I still want to show you how you can check for your local system. We just generate again some trajectory, or simulate some trajectory and case-based data and core sensitivity maps. And in the first time, we just set this environment variable to be 0. So we don't use any FFTW wisdom. That would be also default mode. And then the second step, we set it to 1 and run the same reconstruction. And then we rerun the same reconstruction. So what you see here, so as I said, there's not much performance benefit, but if you don't use any wisdom, you need about 1 second for this reconstruction. If you create the wisdom, because you run it first time, it takes a little bit longer. Here, this is until 2 seconds, but that fluctuates the time because the problem is not that large. And yeah, okay, on the CPU, the estimated optimal algorithm is already quite well. So it's 1.1 seconds again. If you use that wisdom you just created before. But as I said, on other systems, it might have a huge impact. And what you see here is, so it's this, we just show what we have saved. So in the toolbox path, we have the directory save FFTW, and in there we save all the wisdom which was created at one run. The second thing is, which is especially important for 3D, is the low memory modes, as I said. And so I just sketched it here. If you do Pix reconstruction, you usually need to apply the normal operator of the sense operator. So you have some input image. You multiply it with the coils, get the coil images. You do the forward move to go to K-space. Then you do the gridding to go back to the coil images, and then you do the adjoint coils to go back to the image. And here the thing is, like you see, the peak memory you require is if you do it like usually with some oversampling, and we did it with oversampling factor 2. So you will need a peak memory which is large as this 1 times. Okay, here it's just 1 times, so 8 GB of the oversampled coil images. If we use more, like the tuplets trick, it comes down here, then that's more often that. But what we implemented now is like we do the same oversampling with a factor of 2 in each dimension, but we can sequentially compute the NUFFTs. So we just take one, for each dimension, we just take some buffers we need, just not what's the oversampled size. So we try to submit an abstract on this on the SMM, so maybe there are more information, but what you need to know so far is there is a new low mem mode, and you can easily turn it on with -- low mem if you run Pix. And there's a second new option, which is this -- low mem stack option. And there the idea is that we don't need to compute this normal operator for all the coils simultaneously, but we can do it for each coil sequentially. And by that, of course, we set this number of coils here in the peak memory consideration to 1, which again significantly reduces memory, especially for 3D reconstruction. The 8. That's just the bit mask of the coil dimension. So it's 2 to the power of 3. But you can also unroll the Pix about larger dimensions. So if you have a time dimension, you usually can, at least the sense forward model, you can unroll also over that dimensions and compute it sequentially to save memory. I won't run this here. It's because it takes some time on Google Colab, I think. At least here in the end, the last reconstruction takes 1 minute. But you can see here, we do the same reconstruction. Here we simulated 3-dimensional data, but just of dimensionality. I think the coils, you have 32 by 32 by 32. And we run Pix in different modes. So just the normal mode, the low mem mode, the coil stacking low mem mode, and we turn off tuplets mode, which makes it much slower, but again, saves some memory. And you see that here, the results. So in the normal mode for that matrix size, we have 81 megabyte of data needed. If we go to low mem, it reduces to 50, and then to cost data. So it reduces. So I mean, that is a very small problem, so it's not that interesting, but now we consider it on our local servers, like dimensionality, much larger dimensionality, so 256 to the 3 and 8 coils. And there, the first thing, the wisdom makes a huge difference. So if you do it with FFTW wisdom on the CPU reconstruction, you see that's about a factor of 10. So that really depends on your local system, how well FFTW estimates good algorithm, and it makes really a difference. But then if you don't take that no wisdom into account, you see like on the CPU, with each memory saving, it gets a little bit slower, and that is mainly due to, as I said, less efficient parallelization. But you also see how the memory goes down. Oh, sorry. So here we have the CPU memory measured, and it starts at about 24 gigabytes. And if you boil it down to no tuplets and low mem stacking to be 8, then it's think about 3 gigabyte, where you need to think about that only storing the coil sensitivity maps on their own is 1 gigabyte of data. So there's no much overhead of the reconstruction. And we can do the same on the GPU. So if we think about a GPU reconstruction, here on the top is like the CPU memory needed for GPU reconstruction and the CPU time. So the time, so here is just the plain GPU time, the time the GPU needs really so it's lower than the CPU time because there are some pre-computations, and you also see that the GPU memory goes down by using that option. And you see that the parallelization overhead between normal low mem is, I mean, the GPU time is almost the same. And then only if you do the unrolling of the coils, it gets a little bit larger, and no tuplets gets much larger, the GPU time. But yeah, as you see here, we could reduce, again, memory from about 24 gigabytes to 3 gigabytes, 4 gigabytes maybe, which really makes possible to use low efficient GPUs for GPU reconstructions, like maybe something you have in a notebook already. Yes, but we are still on that also to reduce memory then for more, for also, like we have still problems with total variation regularization where we cannot reduce the memory so much. So there is still stuff to do, but we are on that to really reduce memory requirements and work on performance.
Right. So
Yes.
one of the nice things there is that if you have a higher dimension like phases or some other kind of dynamic point, you can change the bit mask there and stack over those instead.
Yes, you can, and can stack over all dimensions basically, which are larger than the core dimension, and all later dimensions you can stack over them right now. So, but still, I mean, that's just the sense part of our Pix reconstruction, and there might be still larger memory consumption also in the regularizations, which we will look at. Yeah.
Mm-hmm.
So yeah, but I mean, the take-home message, maybe you can try something. You reduce the memory by low mem modes, and maybe it helps you to get your reconstruction on the GPU instead of the CPU, which might help you a lot. So I think we have some time left. There would be a small exercise. So we have generated some case-based data and some trajectory in this exercise folder X. But you see, if you do the reconstruction, for example, with NLINV, it might be not optimal because it's shifted, and you need a much larger metric size as is really required to reconstruct that image. So if you want, you can try now to do that more efficient by doing shifting and changing the field of view. or we use again the remaining half hour by question and answer, of course.
Yeah, so thanks very much to both of you. I think this is a really nice kind of addition to some of the non-Cartesian webinars we've done in the past. So just to remind you that some of the past webinars we've gone over some of these non-Cartesian reconstructions, but on a higher level. I think this is a really nice deep dive, and especially this last part, you get really a great factor of savings in memory for small cost in time. It's really worth experimenting with that, especially for 3D data. I think that will help a lot. So I unfortunately have to run. The question is, can this be used with eSpirit, the low memory, and the low memory option can be used in the Pix tool?
So, sorry, can you repeat the question?
Yeah, the question is if it can be used in the Pix tool, and that's I think that's what you were showing, right?
Yeah, it is used in the Pix tool.
Yeah. Right. So this is precisely to serialize the computation of NUFFT as part of this iterative reconstruction. So yeah, that's why it's nice to be able to do that. Yeah, I have to run, but I'll leave it in the hands of Christian and Moritz. So just to reiterate, that we do have like a small exercise that we would encourage you to try to do, and then can take questions on it. But also, if you just have general questions, they can try to help answer them. But thanks to all of you for attending, and I hope to see you all soon again, either in the next webinar or in the next opportunity. And then also keep in mind that the MRI Together free workshop is coming up next week, and we'll be talking there about some open source scientific tools. Okay, thanks very much. Yeah, so stick around for another 30 minutes. Bye.
So I hope that question, like, so it doesn't work with eSpirit, right? But with eSpirit, the Pix reconstruction, you talk about Pix reconstruction by using eSpirit, or?
Yeah, yeah, one question is, how will I know whether the sensitivity map really helped in reconstruction? In other words, if the sensitivity map was not used, what kind of artifacts or I mean, quality reduction I can expect?
I think, yeah, I mean, one option to check that out is to just like, when we do now the Pix reconstruction, we have like a stack of 8 coils, right? So, but we could reconstruct each image of each coil separately. And I think one way, I think already John mentioned that in the chat, is to just split up the separate coils of your K-space and do the reconstruction on that, either with Pix or just with the inverse NUFFT. And then you can compare. I'm not sure. I did not run the reconstruction here in the Google Notebook. If Christian can just try to prepare something to show difference for the.
I'm working on it.
Okay.
I will
Thank you very
just
much.
use.
But then there's another question. Pix is sometimes. Yeah, Pix sometimes spelling affair. I just when I did this comparison now, I also looked into that, and I think one huge part of this initialization is the normalization of the data. I'm not sure if that's a problem for you, but what I saw is like we usually normalize data somehow by computing the median of the gridded image. And for computing the median of the gridded image, all the pixel values are sorted using quicksort. And in my measurements, or when I looked at that, that was the main reason for a long waiting time in the initialization. That might, I hope at least, might be fixed by providing a normalization of the data. That should, I hope, be possible. Just check it out, what we have. I think we can turn out.
Okay, so I could actually show something related to this, to the benefit of parallel imaging.
So maybe you can, maybe maybe you can use this -W option to provide inverse scaling of the data and check if that might be the problem. So you provide a fixed inverse scaling of the data, and maybe you run one reconstruction, get the scaling of the data, and then use that one. One other thing is that we pre-compute the PSF for the triplets trick, and before that, in maybe 2 or 3 or 4 weeks ago, that was always done on the CPU instead of the GPU. But now we have this GPU gridding option, so we can also compute the PSF on the GPU. So that is the other point. So if you try this minus GPU gridding option and the -W option, then I don't think that there's much more from the pre-processing state. But I cannot promise. Yeah.
Did you just bail? Did you talk about exporting and importing the PSF?
No, I did not.
Okay, yeah, I think if it turns out that it takes a long time for you because of the PSF calculation and not because of the scaling, then I haven't used them myself. That is the caveat. There are these PSF export file and PSF import file. So options which you could try if you have multiple reconstructions with the same trajectory. You could try to use PSF export file once, and then in the subsequent reconstructions, always use this pre-calculated PSF, which then should also skip PSF calculation, which might also speed up.
I hope it's fast on the GPU. I hope it's fast now on the GPU. That's
yeah, exactly. If it's faster, I mean, if you're going to do non-Cartesian reconstruction anyway, and then the PSF calculation should not be the slowest part of your reconstruction.
Okay, you want to take over?
Yeah, I could show one thing about parallel imaging. Yes, I want to stop your screen sharing, and I want to share this one. Please share. And wait, which screen can you see? No, you see the wrong screen.
We see your screen.
Yeah, but which one? Why can I not see which screen you see? Do you see the Jupyter Notebook? Okay, Zoom lied to me and told me that you were going to see the other screen. If you see the Jupyter Notebook, everything is fine. What I tried now is basically try to solve this problem without sensitivity calculation. So what I did is I just created an array of ones in the correct size, 220 by 220, and then a 1, then 16 in the 4th dimension, and ran Pix with that. And in that case, you can see, okay, I get a bit of a worse image, but this might be a bit of an unfair comparison. A bit of a fairer comparison would be just to use the NUFFT reconstruction, and I didn't prepare that yet. So in that case, we would just use the inverse NUFFT of the data. And wait a second, I already did that. I just need to scroll around. Sorry about that. What did I do it? Here. So NUFFT spiral is the one I want. So what you would do is use, well, if you have.
No, we don't, or at least I don't see any screen.
You don't see any screen? Share screen?
I'm sorry.
Yeah, no, good that you're telling me that. I want to share that one.
It's there. But the Zoom is inside. Yeah.
Okay. Sorry, then maybe you didn't see this. This is what I talked about. So if you just used ones That is the problem that you get without any call sensitivity profiles. Otherwise, we could look at the RSS. So someone think about how do we combine our 16 coil images into one image. A common choice is root sum of squares. So we also do the same thing here of our just the inverse NUFFT, and let's take a look at that. Maybe let's also put it in here. We could see that in this case, actually, we don't get a huge benefit from parallel imaging. Because our RSS image of the NUFFT is basically looks the same as our parallel imaging reconstruction. Let's get these two together, then we can see even more that it's similar. That shouldn't be surprising, because if we go back to, I showed you the trajectory before. This is the case-based trajectory. It's sampling case-based pretty densely. So we already have a well-sampled case base. We basically do not have any undersampling at all. So yeah, here we don't get a large benefit from parallel imaging. I still want to show this data set just because it is quite nice that another group used the same definition, and I could show you with real data that like it doesn't matter. None of our tools are married to the radial trajectories that we use most commonly, but we can just put in spiral data as well, and we can also get good reconstruction results from that.
Thank you.
Sure. More questions? Somehow Zoom stole my chat tab again. There we go.
Let me tell my story. I'm doing 3D spiral, and I'm doing a lot of undersampling, like 50% undersampling, and I don't see any artifacts other than lower resolution. I don't see artifacts as seen in Cartesian. So I'm not sure what will Pix do for undersampled non-Cartesian actually.
To be honest, 50% undersampling in 3D, you might not. I might think that if you do it in non-Cartesian way, that you might not see any large differences, because you're like, I mean, you're not going to have like these strong coherent artifacts that you know from Cartesian imaging, where you basically have the image shifted by 50% in there, stuff like that. Obviously, and so you might just get a tiny bit of blurring from
Sure, yeah.
from your undersampling. I wouldn't expect anything else. I mean, 50% undersampling in 3D, I think is not a lot. I would expect that if you go to higher undersampling factors, you are going to see more of an issue.
Okay, I'll try that. In that situation, maybe the Pix might be helpful.
Yeah, sure.
Okay. I think you mentioned the on sensitivity map, the outside the brain is not 0. If we mask the background as to 0 on the sensitivity map, will that be helpful?
Probably. I mean, it's not like really a problem here, so I didn't do it, but you certainly could. I mean, the only thing where you see any issue is that there's like a tiny bit of white up here, which would go away if you mask it. Yeah, it's not going to break anything. It's not going to help overly much. But it might be a good idea in cases like this. But then, of course, what you need to do is you first need to reconstruct. Then you need to see where your image is. Then you create sampling mask, and you need to go back and reconstruct again. But like the image in here is probably not going to change.
One of the difficulty in doing spiral imaging is to adjust the gradient delay. Is there any function or tool to help that? tuning?
Yes and no. We have gradient delay correction using, I think, quite interesting methods implemented in BART, but so far they are only going to work for Cartesian data. If you have like some parts of your data that look radial, I'm not sure what exactly your spirals look like, you might be able to use them as well.
Yeah, my initial part looks like radial, right? Yeah.
Yeah. If it looks like that, then you could just like try to run this gradient delay estimation on that. Unfortunately, I don't think we so far extended it to 3D. Yes, we are not really like we're more interested in like fast imaging, so we are mostly doing 2D or maybe stack of stars. We haven't really done like any Kushball or 3D spiral imaging by ourselves. So that might be an issue, but we could work on that. And the last part is then you would need to generate a trajectory with the gradient delays corrected. And yeah, we do. I'm certain that we do not have your 3D spiral implemented in BART right now. I think that's actually one of the problems, that like this trajectory calculation is somehow there are so many different ways of doing it that yeah, we only support the ones that basically lots of people use or that our sequence uses.
Okay.
And it's a bit of an issue.
Thank you.
I mean, it's certainly an interesting problem, and I think nothing really prevents us from using our methods also for 3D radial data, and then by extension for 3D spirals such as yours, but we just haven't done it yet.
Yeah, okay, thank you. I posed a question about the flow imaging case. So because sensitivity map is complex, so if we are measuring velocity curve, then I think we should only use one sensitivity map for all different temporal frames. Is that right?
I think so as well. I would need to check with my colleagues who have done a lot more, flow imaging than me. But if I understand them correctly, yes, like at least for the images, the two images from which you want to do the phase difference, you will need to have the same color sensitivity profiles. So if you're using reference encoding, you can, yeah, you need to do that. But if you're like doing it, I'm sorry, you know what I mean. The things where you need to, where you do phase difference, need the same color sensitivity profile.
Okay, thank you. I have a little bit different question. I tried BART 2.8, and the same NUFFT fails on BART 8. So when I switch back to BART 7, it works again. So what is that?
Okay, BART 8, the release, or do you get an error, or do you get
just the command command error, something like that. So
oh, it's in the chat, or no?
I didn't really check too much because I switched back to 7 hastily.
Yeah, it worked. Yeah, but so did you get an error message, or did you just get a bad reconstruction?
So error message, BART command error.
BART command error. And did you get the, do you still remember the message?
No. I was in a hurry, so I switched back to 7.
Okay. Yeah, maybe, I mean, it would be great if you can just then
Sure.
send an email or something like that. Or,
Okay.
I mean, you can do it via the mailing list, or of course also private to one of us. Like,
sure, I will.
probably.
Okay.
And in the best case, you also provide data, or at least the dimensionality of the data that we can try to reproduce the error. If it's protected, then it's of course a problem. but then dimensionality might help if it's related to that.
Sure. I really appreciate the low memory part because that's a daily practical problem I have.
Yeah, I appreciate that. Yeah, thanks.
But
There is
I need the e-split as well. I mean, I have to manually circle around coil channel because of the same problem.
Oh, you do a spirit,
Yeah.
and then you do the coils for each independently.
Like your coil loop, I have to do that way to avoid the memory.
Oh, that probably, Christian, am I wrong? That probably doesn't work.
Wait.
Because then you have different phases of the coils.
Right. Yeah, I noticed something does not work well, but because of a memory issue, that was the only option I can do.
We have some low memory script for that, but I'm not sure if it helps for 3D data.
Yes,
it was supposed to,
great
but
John was still here because John teased, like when we talked about what we're going to do in the seminar, one way of doing exactly that, getting correct phases in with eSpirit, even with if you do, oh, you're doing coil by coil. In that case, I think it might be difficult. Yeah, in that case, I'm not sure how to do it properly.
I mean, one shot would be using NLINV because it should scale well with memory. So I think it's worth a try. Exactly what Christian just showed.
Yeah, exactly. You could try exactly what I showed, gridding a low resolution, or that using NLINV with a low resolution part and then blow up the coil sensitivity profiles.
Mhm.
But is that going to help your memory issue? Like, can you run the full parallel imaging reconstruction?
Well, Pix works, but the eSpirit does not work.
Okay, yeah. Then you could actually try exactly what I showed here,
Sure.
using NLINV with -X and then a I don't know, 32 by 32 might work or something similar.
Yes. Okay.
There was another question in the chat. Is it possible to jointly reconstruct multiple non-Cartesian 3D datasets where the relative phase between each 3D image should be conserved? I mean, the first thing, if you do multiple 3D, so I assume you need to use the same coils, because otherwise you will get different relative phases because so it's not clear where the phase is in the coils or in the images. And I assume that another point where you want to have you also need to have the same scaling of the data. So there is, I just take again the share screen. If we or maybe it's not that important. I must say I'm not sure. But usually if you do independent reconstructions and want to do something with them for comparing, so as I said in the beginning, we normalize our data usually in the beginning. And after that, so you basically have two options if you want to compare different reconstruction, like point-wise. So one thing is after reconstruction, rescale the image. So you can give this -S option. But of course, if you estimate the phase, then probably the scale of the image should not make any difference. But what might be a problem then is also that the regularization strength is differently because of different scaling of the data. So probably if you want to do independent reconstruction, you should either do -S or provide one scaling for all the reconstruction. So that was the inverse scaling of the data. You should probably fix it and not estimate it from each data set independently. But then if you use the same coils and provide one inverse scaling, then it should work, if I get the problem right.
Yeah, I just wrote one chat. So in 3D spiral, we have Gibbs artifact, which is a circle, basically. So in Cartesian imaging, we have a sub-voxel method to reduce Gibbs artifact. Is there any method developed in non-Cartesian method similar to sub-voxel idea?
So you want to do a subvoxel shift just of the image, or I'm
Yeah,
sorry,
to
but
correct the Gibbs artifact in spiral case. Gibbs artifacts in Fourier is ringing in one direction, but in spiral it's a circle. And sometimes that's pretty bad because it leaves a dark hole in the middle of the object.
and it helps to do a shift in image space, or
In Fourier imaging, there's a technique of a sub-voxel shift method to reduce Gibbs artifacts.
yeah, I'm sorry, I don't know that method, so probably
Okay.
I cannot help you.
Sure.
Yeah, same. I'm sorry. I'm not familiar with the problem.
Thank you. Hi, Christian. I was enjoying your cat behind you.
Yeah, I'm on Linux, so the neither the blurred background and the nor like the BART logo board. I tried to also dress up with the BART t-shirt, but yeah. So of course you could see my cat running around. You can still see.
Where is it?
There still is one cat.
Okay. Sleeping.
Yeah, the perks of working from home. Okay. I think I also need to leave. But I think there were also no more questions. So is that correct?
I
Any
had
last
a
minute question?
question. It's not directly related to non-Cartesian, but in general, or like for it's for the if you do Pix reconstruction with local low rank, and or if I want to add a different regularization, like you have, I'm going to quick check, you can do what L1 Fourier total variation. If I want to do like principal component PCA and then threshold that, is that possible as a regularization?
That's similar to low rank, right? Like, do you want to do it on the entire image?
So I have a series, I have a time series. And so we're actually doing spectroscopic imaging. So like for one example, it's 2D spatial, third dimension is spectroscopic encoding, and then time dimension.
so the spectropic dimension is a time dimension, or are these
no,
other?
It's I have 4 dimension.
Okay, 2 image, time, and spectropic. Sorry,
Right.
I cannot pronounce it either.
Yeah.
So I think right now we don't have that, not PCA based. I mean, in general, I can now give the cop-out answer. We can include a TensorFlow graph, so we can include everything that is included in TensorFlow, but no, we don't have it right now.
But isn't PCA a locally low rank? I'm sorry. I thought like that does, like we do SVD threshold the singular values and then go back. Isn't that local low rank or low rank?
How do I? But
think
only wanted, so the way what we're working on is just doing having the low rank on the whole 3D, two spatial plus spectroscopic dimension over time. But since we have like within the spectroscopic dimension a lot of the intensity differences, like you have one large peak dominating, we want to do the principal component thresholding, like sparsity thresholding, along for each spectral point separately.
Okay, so you basically want to loop over this spectrum dimension, and then do separate, like have a PCA in the pixels versus time dimension. Do I get that right?
Yeah, I think yes.
So you basically the different spectroscopic points you want to treat them independently.
Yeah.
Okay. I need to check. I can just try to share my screen. I must, to be honest, I'm not sure if that's already
It's
possible.
okay. I mean, it's already late. I don't want to.
I have some time left, so for me it's fine. It depends on you. But to share my screen. So when we look in the help of the regularization of Pix. Okay, there's not really a help. Okay, it might be really just using the local low rank option, but I'm not sure. So maybe you can kind of repose that question in the mailing list, and then we will answer to that, or try to find out if it's possible at all.
I'll try. Like I didn't. Maybe this is possible. And if I don't get it to work, I'll ask the question. Thanks.
Yeah, great. So if not, it should be possible to include that, because if I get it right. Yeah.
Thanks. And in general, thanks for providing this tool and the webinar. It's great.
Yeah. Thank you for that. You're very welcome. Yeah. I think if there are no further question, we can end the meeting. And I hope to see you again at upcoming webinars, and also at the appointments or dates John mentioned in the beginning. So goodbye. Have a nice evening, or whatever, in whatever time zone you are. Have a nice day. Bye-bye.
Okay, thank you.
Can I ask maybe one more question? Sorry.
Sure. I'm still there.
So about this scaling factor again. So if I use this -s flag, then I should be able to have my initial pixel values back. Is that correct? Because, so for the Pix reconstruction.
Yes, it should work. So we rescale the image after the reconstruction. So I mean, you might still have a scaling from the
scaling is based on the median. How exactly is this done? So is there an initial reconstruction?
Yes. So I'm not entirely sure about all the factors, but what happening is we do the adjoint of the sense forward model, apply that on the k-space
Mm-hmm.
to get the image. So if in the Cartesian case, it would be a zero field reconstruction basically. And then we somehow, yeah, I don't know what we really do, but we compute the median or maybe also the quantiles, and based on that we scale the data. And the idea behind that is that if you scale the data to one common scale, then the regularization strength depends. I mean, if you do L1 regularization, the all L1 regularization, the lambda factor depends on the scaling of the data. So therefore, we choose some common scale of the data to be able to fix somehow the L1 parameters, the regularization strength. So therefore we scale, and then if you do the rescale, you get back, yeah, to the image. Should be, I mean, if you do L2 regularization only, it should be equivalent to do the scaling, and then so with the -s option to do the rescaling, should be equivalent to use -w with 1. So you just downscale the data at all. So L2, that should not make any difference. But for L1, it makes a difference because it changes your effectively your regularization parameter.
Okay, and so -w1 would be no scaling at all. So I would,
Yes.
so I would override basically these internal scalings.
Yes.
Okay, okay, that's good to know.
Yeah, it's always a problem when you compare different reconstructions there. Yeah, if you want to do some phase difference or something like, no, not phase difference. Yeah. So yeah, it is good to know.
Okay.
I mean, when I started with BART, I also ran in that problem. I was wondering, wait, that doesn't make sense. I just have a reconstruction, multiplied that with the coils, do the FFT, and I don't get back what I put in. So
Yeah.
but that's the scaling. Yeah.
Okay, great, thank you.
Yeah, you're welcome. Okay. Maybe some other question pops up now. Twice. Last chance.